So we're now going to go across the pond, but in the opposite direction of
Yes.
the pond that people normally associate with that phrase, from California all the way to Beijing, where we have learned that diamonds have gotten an upgrade. My wife immediately texted me when she saw the stories for today.
Oh, nice.
And was like, I want you to tell me about this one after you're done.
Nice.
This is out of the Center for High Pressure Science and Technology Advanced Research in Beijing, where apparently scientists are able to create extra hard hexagonal diamonds in the lab that are up to 60% stronger than normal diamonds and can be used to create super tough drilling and cutting tools for industrial applications. Sorry, honey, this is not Tiffany's.
No.
But interesting nonetheless. So help me understand what exactly is going on with this new lab-grown diamond stuff.
Yeah. So diamonds, girl's best friend.
Yes.
Usually when we think about diamonds, we're thinking about the thing that you're going to buy for your girl when you want to get the government involved.
Yes.
You know?
Yeah, we love the government involved.
The diamond is a pure form of carbon.
Okay.
Okay? Something called an allotrope. There's nothing other than carbon in diamond.
Okay.
Okay? Which is pretty cool.
That's pretty cool.
There's very few elements that actually do this kind of thing, where they form like a solid that is only that. And it's like a compound. Like metals, I guess, do this, but they're not like bonded in the sense that like diamonds are bonded. Like these are covalent bonds between carbon atoms that make it so strong. There's other allotropes of carbon, and every time there's an allotrope of carbon, it's like it does amazing things. We've got carbon nanotubes, which are like these like tubes made out of entirely of carbon. That's the carbon fiber that you're like that we see in Formula One and things like that.
Yep.
There's buckyballs, the Buckminster Fullerene.
Yeah, my favorite.
The soccer ball, right?
Yeah.
Made out of carbon.
Yep.
There's obviously also graphite, which is the thing in your pencil lead, and graphene, which is a single layer of graphite. That one won the Nobel Prize many years ago because that has like extraordinary electrical and conducting properties.
I think Batman's suit is based on graphene.
Graphene? Yeah, I can imagine. It's a it's like one of those things that you can use in movies, right?
Yeah.
Because there's so many unexplored things. Like, oh, quantum this, like,
It
yeah,
grabs
just
you.
say it. Yeah, you know? Like, graphene is one of those.
Yeah.
Where it's like, there's so many unexplored areas for graphene that you could just be like, yeah, maybe it's made out of graphene. So diamond is one of those things. It's called an allotrope, where you have this, like, pure elemental covalently bonded form. And it is the hardest thing that we know on Earth. Okay? On the Mohs hardness scale, it is, like, by definition 10. Because it's the hardest thing. And it's used in industrial applications. If you want to like cut stuff, like you use a diamond, right? If you want to cut like really, really hard things. We used to think the diamond was the hardest thing. And like we had sort of exhausted the possibilities on all the things that carbon could be. Okay. And then people started looking at this thing called the Canyon Diablo meteorite, which is the meteorite that fell on Arizona 50,000 years ago. Have you been to Meteor Crater?
I know of it. I've never been.
Yeah, it's right off the I think it's off the 40 freeway.
40, yep.
Yeah, on your way from like Grand Canyon to Albuquerque. It's a wonderful place. It's the best preserved meteor crater on the planet because in these arid conditions you see this beautiful. It was also only 50,000 years ago.
America always has the best.
We always got the best. Yeah. And so it was also like one of the first places that my dad visited when he came to America from India. So I remember when I was like in India, I was like seeing like photos of the meteor crater going like, that's crazy, you know? So people found the meteorite for this thing. It's a massive meteorite called the Canyon Diablo meteorite, 640 kilograms. And in this, people started doing like chemical analyses, and they thought they saw another form of a diamond. Okay. It was called Lonsdaleite. Okay. And it was this elusive hexagonal thing that people had theorized existed, but maybe it was in there. Very trace amounts. And there was controversy, like, are you really seeing what you're seeing? Like, is this real? People started doing theoretical modeling of it and were like, this thing would be even harder than diamond if if it was true. The hypothesis is that whatever carbon was in the meteorite, it slammed, like this meteorite was so big that it didn't just like burn up in the Earth's atmosphere, it actually slammed into the ground, right? And when it slammed into the ground, that carbon in all that high temperature and pressure fused into this new form.
Which makes sense.
Of Leon's, yeah, and it makes sense. So, and you see these like trace amounts, but ever since then, people have been on the hunt to try to make this thing, okay? Because it's going to be kind of like holy grail for material science, right? You're going to get even harder than diamond. You're going to get novel electrical properties. Perhaps you can start using it in like quantum computers and like all sorts of stuff, right? So you want to try and make it first. But it ended up being extremely hard to make. Okay. The reason for that is people were basically trying to put carbon under a lot of stress to hope for making this like structure.
They should just put them in Princeton during grade deflation. That'll be plenty of stress.
Dude. Yeah. During finals week, easy. That's where diamonds are made. So they're trying to make this hexagonal diamond.
Yes.
Right. The normal diamonds that we have, those are called cubic diamonds. Okay. And that's because like the way that the bonds all work, it looks like it's got this like cubic form that repeats over and over. In the hexagonal diamond, you're gonna get hexagonal close packing, where like the bonds are now slightly different, but in this like weird hexagonal heterostructure that like with like two different bond lengths that becomes extremely nice and tight. So you're trying to make this thing. Everyone's process is basically the same: high stress, high temperature, high pressure. What these guys did was they were like, we need to control this thing really, really well in order to actually make it. Okay. So their setup is actually kind of crazy. Their setup is they've got a diamond anvil press. Okay. They're trying to reach pressures that are insane. 200,000 times the atmospheric pressure. Okay. Yeah. So Marianas Trench is like 1,000 atmospheres. This is 200 times the pressure that you see in Marianas Trench.
The highest pressure in the natural environment that we have.
So how do we achieve that pressure without blowing everything up?
Right.
Well, you use the best thing there is, which is a diamond. You make a press out of diamonds.
Oh my God.
It's called a diamond anvil press.
Diamonds on diamonds.
Yeah. They're using the old diamond to make the new diamond.
That's so funny.
Right?
Yeah.
It's kind of cool. So they've got this diamond anvil cell that goes in like this, okay? And in that you can now start squishing everything, so it goes to extremely high pressure. Inside that thing, they put in a single crystal of graphite. Okay, this is like the lead in your pencil is graphite, but it's not a single crystal. It's usually like sheared layers, which is why like, you can like write with it like shears off. This is a single crystal, so you've got these hexagonal lattices that are on top of each other that are connected by van der Waals forces, which are like just loose forces. They're not covalently bonded.
Got it.
Like the layer within the layer itself, these hexagons are a bunch of carbons that are covalently bonded, but the two layers are not covalently bonded. Understood. What we want to get is hexagonal layers that are now covalently bonded in like this like crazy hexagonal sort of crystal, right? So they start with a single crystal like that. They pump it with all this pressure. They have lasers that are heating it through the diamond.
Always have lasers.
When all has failed, just shine some lasers on it, heat it up. So they're heating up this thing to like 1,000 to like 1,500 degrees Celsius. Yeah. So like 2,000, 3,000 degrees Fahrenheit. And then they create this structure that they think is this hexagonal diamond. And not only that, they haven't created like trace amounts. They've created something like that's as big as a millimeter. Which sounds like small, but like, dude, that's what, 10 to the 20 atoms.
Yeah,
it's a lot.
Yeah.
That's a lot.
Yeah, and also it's a novel technique.
Yeah.
Right. So they have to like first create
even a even a millimeter's worth, right? Like people had done way less. Right. Where like you got to go into with the electron microscope and be like, hey, right there, see, like that little part there has got a hexagonal diamond.
That's a diamond.
Yeah. But here it's like, okay, a millimeter, I can like see that with my naked eye. Yeah. So they finally did this, and the first thing everyone's gonna do is say, nah.
Yeah. Right.
You didn't do it.
Right.
So they, again, just like those previous stories that we've had, we're going to run through a suite of tests to make sure that we're talking about what we're talking about. So they did X-ray diffraction, which is the idea of shooting X-rays at a crystal. The X-rays are going to diffract in a certain way, and depending on the crystal structure of the atoms, they're going to diffract and create an image of where the X-rays bounced off. And that'll tell you sort of the bond spacing and like the bond angles and things like that. Things match.
So you can know if those hexagonal layers actually like ended up covalently bonding.
And like the spacing of it, like is it 1.5 angstroms, is it 1 angstrom, like down to like, you know, hydrogen like atom length type stuff. They also do high resolution transmission electron microscopy. That's just the standard thing. You got to put it in there. You got to see, you got like the little hexagonal structures. So that's nice. They also did something called Raman spectroscopy, named after C.V. Raman, my guy from India, the first Nobel Prize winner in physics from India. Raman spectroscopy is the idea that molecules vibrate, right? And so in normal spectroscopy, you want to see, you shoot in some light, and then like you're going to go to a high quantum state, the lower quantum state, and then that's going to release some energy, right? Here, some of the light that goes in is going to get like lost into the vibrational modes of the molecule, and then you're going to get a different color of light that sometimes might be even higher, because like the vibration is going to like dump like some energy and stuff like that. So you get this inelastic like sort of scattering where the weird energy happens when you start doing this kind of stuff. So they did that, and they found 3 vibrational modes. So like, one this way, one like that's longer, which confirms that there are 2 different bond lengths, which is what the theory suggests. Like when you go and you do the crystalline structure, you're like, there should be one bond length that's at 1.58, which is the intralayer one that's like within the buckled honeycomb layer, and then there's 1.50, which is linking one layer to the other, and these 2 should be different lengths. And the Raman spectroscopy, you do the simulation, and you find out that it is in fact there, right? So they're doing all of these things, and it's kind of a crazy story, because actually earlier this year, another Chinese group came out saying that they had a plan. Concept of a plan to they had this like promising procedure to make this hexagonal diamond. Okay, and they were like, we're gonna have like y'all wait. And then I think these guys scooped them. That other group was from University of Shanghai, and these guys from Beijing. Like, so I mean, it also shows just how far China has come as a scientific powerhouse. Where like they're scooping within their country now. Right.
Not even in the global competition.
Yeah. Now it's like they're competing amongst themselves. It's actually like they've advanced so much that now they've got competing institutions that are like, now they're like having beef with each other
and pushing the boundaries of the frontier of science research, which is like, that's actually very interesting. And because I know there's a lot of, in the popular discourse, there can tend to be this knee-jerk reaction when referring to Chinese studies, because there's the geopolitical nexus here, which creates an incentive for there to be cutting corners to be able to show advancements happening. And so a lot of times, again, in the zeitgeist conversation, it's like, well, the Chinese study comes out, the data may be faked, and take it with a grain of salt. It's kind of like the response.
I mean, but this is published in Nature. They did all of these tests.
And I think that perception, it's the same thing with like the same idea with looking at China from the trade secrets perspective, where maybe 15, 20 years ago, it was true that, and there still is, obviously.
And there probably still is,
However, that is an independent point to the fact that they've now established their own flywheel of educating a large amount of their populace in the fundamental areas of science, mathematics, etc., necessary to then populate these institutions with people to do these studies, and then actually funding those institutions to be able to get results. And like that infrastructure exists independent if there's some funny business going on in some cases. There's like a blanket, I think, shutting off of like really taking in earnest things that are coming out of here, which I think is not a great thing for us to do from just a strategic surprise perspective.
No.
Because what we don't want to do is underestimate.
Yes.
And then there's now this runaway, because like progress compounds, right? And we don't want to have this runaway train where with what we're seeing with manufacturing in the U.S., where we didn't care about it, and then now we're like, oh, we need to re-onshore, and it's like,
yeah, it's like now it's impossible.
It's too late.
Yeah, like the global economy is already gone 30 paces ahead, and this is what it is, right?
And so
and if you don't like it, just like fun science.
Yeah, correct.
Right?
Correct. If we're in this great power war with China, one of the like battlefields is frontier research.
It always is.
It always is.
Yeah, anywhere.
That's how we won World War II.
Yeah,
and how we lost the idea that it's important when it was literally the reason we became the global world power that we are still baffles me.
Yeah.
That's a digression. But important context, because a lot of people show China studies shut down, right? And this is why we talk about it from first principles, because you can
they did it. They did the work.
They
did the work. Like they got hexagonal diamonds. This has been something that people have been after for 50 years, and they got it. You're right? Like in material science, this was kind of like that thing on the hill that you want to get to. And they got it. Yeah.
And not only did they get it, they're potentially on pace to get it twice before anyone else. If that other university that wasn't beaten up by the Beijing also did it.
Yeah,
right?
they probably shouldn't have published like that early. Like I wonder if like that gave. Oh, that's what we were missing.
Like they were already almost there.
Yeah.
Oh, let's just change that to a 2. So unfortunately for this use case, we're not gonna get cheaper diamonds to put on ring fingers.
No. Cheaper diamonds are actually already here. We have lab-grown diamonds. The lab-grown diamonds actually one of the processes that they use for lab-grown diamonds is this high temperature, high pressure. But then there's a much more effective and cheaper way to do it, which is chemical vapor deposition.
Okay.
Which is interesting, where you have like a diamond sort of seed, and then you fill the chamber with stuff. Like usually it's like methane. Okay. Which is CH4, so carbon and hydrogen. And then you start heating up the methane with lasers to take out the hydrogen. Yeah, and then the carbon just like finds its way on the diamond, and then you grow it layer by layer to make a lab-grown diamond, right? Like the only reason diamonds are expensive is because the De Beers Corporation has a monopoly on it. And now they're like putting out this like propaganda saying like, oh yeah, but you want one from the earth, that's actually caused human suffering. Yeah. Because otherwise your wife is not going to know that you love her.
Right. True love comes from the human suffering of minds all over Africa that are getting you these earth-grown diamonds.
Yeah. Otherwise, what is this all about?
No, that is what they say.
Yeah.
that is what they say. Great story. Diamonds getting an upgrade. Crazy industrial use cases.
Yeah, it's going to be cool.
Implementation to get to the answer to what has been a 50-year-ish quest to be able to actually experimentally
realize
that this hexagonal diamond was possible. And you did bring up as an analogy or as a reference point that things like, if you can do the hexagonal diamond, maybe there are use cases in other technologies, maybe like in quantum computers, which
or like in industry, like you always want harder things.
Right. Drilling is obviously going to be a use case.
Easy.